Welcome! In this session, we'll dive into the problem number 497, random point in non-overlapping rectangles. This is an intriguing challenge that involves selecting random points within specified rectangles while ensuring efficiency and correctness. We'll explore different approaches and analyze their complexities. Let's get started. In this problem, we are tasked with designing an algorithm to randomly pick a point from a set of non-overlapping rectangles. The rectangles are represented as an array where each rectangle is defined by its bottom left corner, x1, y1, and top right corner, x2, y2. The algorithm must ensure that every integer point inside a rectangle has an equal probability of being chosen. Additionally, the solution should handle up to 10,000 rectangles efficiently. The implementation involves creating a class called solution with two main components: a constructor to initialize the rectangles and a pick method to return a randomly chosen point. The probabilities of selecting points must be proportional to the area of the rectangles they belong to, ensuring fairness in the selection process. The output of the algorithm is a randomly selected point, px, py, such that it lies within the bounds of one of the rectangles. For instance, consider the example where the input contains a single rectangle defined as 1, 1, 5, 5. This rectangle includes all integer points from 1, 1 to 5, 5. When we call the pick method, it will output a random point such as 4, 3, or 1, 1. Since there is only one rectangle, the algorithm will ensure that each point inside it is equally likely to be chosen. This demonstrates the core requirement of uniformly selecting points from the given rectangles. Now, let's look at an example with multiple rectangles. Suppose the input consists of two rectangles, -2, -2, -1, -1, and 1, 1, 3, 3. The first rectangle spans the points from -2, -2 to -1, -1, while the second rectangle includes points from 1, 1 to 3, 3. When we call the pick method, the algorithm may generate points such as -2, -2 from the first rectangle or 2, 3 from the second. Importantly, the probabilities of selecting points from each rectangle are proportional to their areas. In this case, the second rectangle has a larger area, so points within it are more likely to be picked compared to those in the first rectangle. In a more complex scenario with three rectangles, such as 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4, 4, 4, the algorithm must handle rectangles of varying areas. The first two rectangles each have an area of 4 points, 0, 0 to 1, 1, and 2, 2 to 3, 3, while the third rectangle contains only a single point, 4, 4. When the pick method is called, the algorithm might produce outputs like 4, 4, or 0, 1. However, because the third rectangle is much smaller, the probability of selecting its single point is lower compared to points in the first two rectangles. This ensures that the selection process remains proportional to the areas of the rectangles. To summarize, the problem comes with several constraints and edge cases to consider. The input can have up to 10,000 rectangles, each defined by 4 integers, and their coordinates can range from -10⁻9 to 10⁻9. The rectangles are always non-overlapping, and the algorithm must handle up to 10,000 pick calls efficiently. Edge cases include scenarios with only one rectangle, rectangles of vastly different sizes, or rectangles containing a single point. Additionally, the algorithm must work correctly for the maximum constraints, such as a large number of rectangles or extremely large coordinate values. By addressing these constraints, the solution will ensure accuracy and efficiency across all possible inputs. To begin addressing this problem, one possible approach is a brute force method. The intuition behind this method is straightforward. We first randomly pick a rectangle, and then randomly select a point within that rectangle. To achieve this, we calculate the total number of points across all rectangles by summing up their areas. Once we have this total, we generate a random index within this range. The next step is to determine which rectangle contains the randomly chosen point. This requires iterating through all rectangles and their cumulative point counts until the correct one is identified. Finally, we compute the exact coordinates of the point relative to the selected rectangle. However, while this approach is conceptually simple, its time complexity is O(n) per query because of the need to iterate through all rectangles. This becomes a significant bottleneck as the number of rectangles grows. Additionally, it has minimal memory requirements with 1 space complexity, but its inefficiency makes it less suitable for larger inputs. To improve upon the brute force method, we can use an optimized approach leveraging prefix sums. Here, the intuition is to pre-process the total number of points in each rectangle and store these cumulative values in a prefix sum array. This allows us to efficiently map a randomly generated point index to its corresponding rectangle. The steps for this approach are as follows. First, we calculate the number of points in each rectangle and build the prefix sum array. Then, when a random point index is generated, we use binary search on the prefix sum array to quickly identify which rectangle contains the point. After locating the correct rectangle, we use modular arithmetic to determine the precise coordinates of the point within that rectangle. This method significantly reduces the time complexity to O log n per query, thanks to the binary search after an O n pre-processing step. While the space complexity increases slightly to O n due to the prefix sum array, this trade-off is negligible compared to the speed gain. Additionally, an alternative approach using weighted random sampling can achieve similar efficiency by treating rectangles as weighted regions. However, it may require more complex implementation or external libraries, making the prefix sum approach generally preferable for simplicity and maintainability. The chosen strategy for solving the problem is the optimized approach using prefix sums. There are several key observations that make this approach ideal. First, because the rectangles are non-overlapping, we can consider all the points as part of a single, continuous sequence. This allows us to map any random point index directly to its corresponding rectangle using the prefix sum array. The use of binary search to perform this mapping ensures that the lookup is both fast and efficient. The aha moment here is realizing that instead of performing a linear search through rectangles for every query, we can pre-process the cumulative point counts once and leverage this pre-processing for rapid queries. This strategy was chosen because it strikes an excellent balance between simplicity and efficiency. It avoids the complexities associated with weighted random sampling while still achieving an impressive O log n query time. The pre-processing step, which is O n, is quick and scales well even for large inputs. While there is a minor trade-off in terms of additional memory required for the prefix sum array, this is a small price to pay for the significant gains in performance. The slight increase in implementation complexity compared to brute force is more than justified by the overall efficiency of this method. In conclusion, the prefix sum approach is the optimal strategy for this problem. It offers the best balance between efficiency, simplicity, and scalability. By avoiding the inefficiencies of the brute force method and the complexity of weighted random sampling, it provides a practical yet powerful solution. The pre-processing step is fast, the query time is logarithmic, and the additional memory usage is minimal, making this approach well suited to handle large inputs effectively. Overall, the prefix sum method ensures that the problem is solved in a way that is both elegant and performant. To solve the problem of randomly picking a point within a set of given rectangles, we need to ensure every point across all rectangles has an equal probability of being selected. Each rectangle is defined by its bottom left and top right corners, represented as x1, y1, x2, y2. For example, if we have rectangles 1, 1, 2, 2, 3, 3, 4, 4, the first rectangle contains the points 1, 1, 1, 2, 2, 1, 2, 2, and the second one contains 3, 3, 3, 4, 4, 3, 4, 4. The first step in our algorithm involves understanding this input representation. Next, we calculate the total number of points in each rectangle using the formula x2 x1 plus 1 asterisk y2 y1 plus 1. This gives us the total points a rectangle contains, which we will then use to build a running prefix sum, a data structure that will let us efficiently handle random selection later on. Let's look at an example to solidify this concept. For the rectangles 1, 1, 2, 2, 3, 3, 4, 4, the first rectangle contains 2 minus 1 plus 1 close parenthesis times open parenthesis 2 minus 1 plus 1 close parenthesis is equal to 4 points, and the second rectangle contains 4 minus 3 plus 1 close parenthesis times open parenthesis 4 minus 3 plus 1 close parenthesis is equal to 4 points. By summing these totals cumulatively, we obtain the prefix sum, 4, 8, which represents the cumulative points across rectangles. With this structure in place, we can now randomly select a point index. To do this, we generate a random integer k from 1 to total underscore points, where total underscore points is the sum of points across all rectangles, in this case, 8. Using a binary search on the prefix sum, we can efficiently determine which rectangle contains the point corresponding to k. For example, if k equals 6, we see that it falls within the second rectangle, since 5 6 less than or equal to 8 in the prefix sum. Once we've identified the rectangle corresponding to k, our next step is to determine the specific point within that rectangle. We do this by first finding the local index of the point within the rectangle. This is done by subtracting the cumulative count of all previous rectangles from k. For example, if k equals 6 and the prefix sum up to the first rectangle is 4, the local index is 6, 4 equals 2. Next, we calculate the row and column offsets using modular arithmetic. The row offset is index underscore in underscore rectangle 1 / width, and the column offset is index underscore in underscore rectangle 1% width, where the width is x2 x1 plus 1. For rectangle 3 3 4 4, the width is 4 3 plus 1 equals 2. Using these offsets, we add the row and column adjustments to the bottom left corner of the rectangle x1 y1 to obtain the exact point. In this example, the point corresponding to k equals 6 is 3 plus 0, 3 plus 1 equals 3, 4. Finally, we return the computed coordinates as the result. This algorithm relies on a few key insights. First, the prefix sum optimization allows us to identify the rectangle for a given point index in O log n time using binary search, rather than iterating through all the rectangles. Second, by treating all points as part of a single continuous range, we ensure uniform probability for selecting any point. Each point has an equal chance of being chosen because the random index is uniformly distributed across the total points. Third, the use of modular arithmetic makes the mapping of indices to points within a rectangle efficient, avoiding the need to explicitly generate all points in advance. The data structures we use include a prefix sum array, which stores cumulative point counts for efficient range queries, and a random number generator to produce the random index k. Let's analyze the complexity of this approach. The pre-processing time is O, n, where n is the number of rectangles, as we calculate the prefix sum in a single pass over the rectangles. Each query takes O log n time for the binary search and O 1 time for the coordinate computation, making the query time O log n overall. The space complexity is O, n, as we store the prefix sum array. There are also a few edge cases to consider. For a single rectangle, the algorithm should correctly handle point selection without any special adjustments. For degenerate rectangles, where x1 equals x2 or y1 equals y2, we must treat these as lines or single points correctly. Finally, for rectangles with large ranges, we need to ensure calculations are handled without integer overflow, particularly when computing the prefix sum. Here, we start by importing the random module and defining a solution class to handle the problem. In the constructor, we accept an input rex, which is a list of rectangles, each defined by its bottom left and top right coordinates. Within the constructor, we initialize three key attributes: self.rex to store the input rectangles, self.areas to hold cumulative area weights, and self.total_area to track the sum of all rectangle areas. The next step is to compute the area for each rectangle. For each rectangle defined by coordinates x1, y1, x2, and y2, we calculate its area. Since the coordinates are inclusive, we add 1 to both the width and height calculations. These individual areas are then added to the running total, self.total_area, and the cumulative total is stored in self.areas. This cumulative sum helps us determine rectangle weights for random selection later. The constructor essentially pre-computes all the data we need to efficiently pick random points across rectangles in proportion to their size. The pick method begins by generating a random integer between 1 and the total area of all rectangles. This random value represents a point within the combined space of all rectangles. Using binary search, we determine which rectangle this random point falls into. The search is conducted on the self.areas list, where the cumulative area weights help us quickly locate the rectangle index. Once we identify the rectangle, its coordinates x1, y1, x2, and y2 are retrieved. To select a random point within this rectangle, we generate a random x-coordinate between x1 and x2 and a random y-coordinate between y1 and y2, ensuring each point within the rectangle is equally likely to be picked. Finally, we return these coordinates as a list, representing the randomly chosen point. Here, we start by importing the necessary libraries and defining our solution class. Inside the class, we declare several private variables. The total area variable will store the cumulative area of all rectangles, while the areas array is used to keep track of the cumulative sum of areas for each rectangle. The rex variable holds the array of rectangles, and we also initialize a random object for generating random numbers. In the constructor, we take the rex array as input and initialize the areas array and total area. To calculate the cumulative areas, we loop through each rectangle, extracting its coordinates x1, y1, x2, and y2. Using these coordinates, we compute the area of the rectangle using the formula x2 x1 plus 1 asterisk y2 y1 plus 1. This formula accounts for inclusive bounds to ensure we count all points within the rectangle. We then update the total area by adding the current rectangle's area and store the cumulative sum in the areas array. This pre-processing step allows us to efficiently select a rectangle later, based on its proportional area. Once the pick method is called, the first step is to generate a random area index within the range of 1 to total area. This random number corresponds to a weighted selection, where rectangles with larger areas have a higher likelihood of being chosen. To identify which rectangle this random area falls into, we use a binary search on the areas array. We initialize two pointers, left and right, representing the search range, and repeatedly calculate the midpoint index. If the cumulative area at the midpoint is less than the random area, we narrow the search to the right half, otherwise, we search the left half. Once the binary search concludes, the left pointer will indicate the selected rectangle. We then extract the rectangle's coordinates and use the random object to generate a random x and y within the rectangle's bounds. The horizontal range is determined by x1 to x2, and the vertical range by y1 to y2. Finally, we return the randomly chosen point as an array containing the x and y coordinates. Here, we are given two rectangles, the first with coordinates 1, 1, 2, 2, and the second with coordinates 3, 3, 4, 4. To begin, we calculate the area of each rectangle. For the first rectangle, the width is 2 to 1 plus 1, and the height is also 2 to 1 plus 1, so the area becomes 4. Similarly, for the second rectangle, the width is 4 to 3 plus 1, and the height is 4 to 3 plus 1, resulting in an area of 4 as well. Next, we compute the cumulative areas, which will serve as weights for selecting rectangles. The cumulative areas become 4, 8, and the total area across all rectangles is 8. Now, for the first random point selection, we generate a random number within the range of 1 to 8, let's say it's 5. Using binary search, we determine which rectangle this value corresponds to. Starting with left at 0 and right at 1, the midpoint is 0. Since the cumulative area at index 0 is 4, which is less than 5, we update left to 1. This means rectangle 2 is chosen. Then, we randomly select a point within rectangle 2's coordinates, 3, 3, 4, 4. For x, we pick a random value between 3 and 4, which is 3. For y, we pick a random value between 3 and 4, which is 4. Therefore, the output is 3, 4. For the second random point selection, we start by generating another random number within the range of 1 to 8, and this time it's 2. Again, we use binary search to find the corresponding rectangle. With left at 0 and right at 1, the midpoint is 0. This time, the cumulative area at index 0 is 4, which is greater than or equal to 2, so we update right to 0. This indicates rectangle 1 is selected. Now, within rectangle 1's coordinates, 1, 1, 2, 2, we randomly pick a point. For the x-coordinate, we choose a random value between 1 and 2, which is 1. For the y-coordinate, we choose a random value between 1 and 2, which is also 1. Hence, the output is 1, 1. Now, let's look at a new example where we have three rectangles with coordinates 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4, 5, 5. First, we calculate the areas. The area of the first rectangle is 4, the second rectangle also has an area of 4, and the third rectangle has an area of 4 as well. Adding these together, we find the cumulative areas to be 4, 8, 12, and the total area sums up to 12. For the first random point selection, we generate a random number between 1 and 12, which in this case is 9. Using binary search, we determine which rectangle corresponds to this value. Starting with left at 0 and right at 2, the midpoint is 1. The cumulative area at index 1 is 8, which is less than 9, so we update left to 2. This means rectangle 3 is selected. Within rectangle 3's coordinates, 4, 4, 5, 5, we randomly choose x and y values. For x, we pick a random value between 4 and 5, which is 5. For y, we pick a random value between 4 and 5, which is 4. Therefore, the output is 5, 4. Finally, for the second random point selection, we generate a random number between 1 and 12, and let's say it's 3. Again, we use binary search to locate the corresponding rectangle. With left at 0 and right at 2, the midpoint is 1. The cumulative area at index 1 is 8, which is greater than or equal to 3, so we update right to 0. This indicates rectangle 1 is chosen. Within rectangle 1's coordinates, 0, 0, 1, 1, we randomly pick a point. For x, we select a random value between 0 and 1, which is 1. For y, we select a random value between 0 and 1, which is 0. As a result, the output is 1, 0. The first step is the initialization process in the __init___ method. Appending these areas to a list is an O(1) operation, and the summation of areas also falls within the overall O(n) complexity. Now, for the pick method, the process begins by generating a random integer to decide the target area, which takes constant time, O(1). Next, we use binary search to find the corresponding rectangle in the cumulative areas list. Combining these steps gives the pick method an overall time complexity of O log n. Here, we analyze the time complexity of our solution. During this step, we calculate the area of each rectangle using the formula x2 x1 plus 1 asterisk y2 y1 plus 1. Since this operation is performed once for each rectangle, and there are n rectangles, the time complexity for this part is O(n). Since the list contains n elements, this search is performed in O log n time. Finally, after determining the rectangle, we select a random point within it by generating two random integers within the rectangle's bounds. This is an O(1) operation since it depends only on the size of the rectangle and not the total number of rectangles. Now, putting it all together, the total time complexity of the solution depends on both initialization and the point picking operations. Initialization is O(n), and each call to pick takes O log n. If there are m calls to pick, the total time complexity becomes O(n) plus m asterisk log n. Shifting to space complexity, the initialization phase requires space for the input list of rectangles, which takes O(n). Additionally, we store the cumulative areas list, which also requires O(n) space since it contains one value per rectangle. Scalar variables such as loop counters and the total area require only O(1) space. For the pick method, no additional space is needed beyond temporary variables used for calculations, so its space usage is O(1). Therefore, the overall space complexity of the solution is O(n), dominated by the storage of the input rectangles and the areas list. To understand the efficiency of this solution, let's compare it with a brute force approach. In a naive implementation, we would generate all possible points across all rectangles and store them in a single list. This would involve iterating through every point in every rectangle, resulting in an initialization time complexity of O(a), where a is the total number of points. Likewise, storage for these points would require O(a) space. Picking a random point from this flattened list would then take O(1) time. In contrast, the optimized approach avoids generating all individual points. Initialization in the current solution is O(n), as we process rectangles rather than points, and the space usage is also O(n) for the same reason. Point picking takes only O log n due to the binary search. This makes the optimized solution much more scalable, particularly when the total number of points is significantly larger than n, the number of rectangles. To solidify our understanding, let's briefly examine the mathematical reasoning behind the time complexity. In the pick method, we use binary search to locate the rectangle corresponding to the random area. The logarithmic complexity of this step arises from the process of repeatedly having the search space, which ensures efficient performance even as the number of rectangles increases. Random point selection within a rectangle is a constant time operation, as it relies only on the dimensions of the chosen rectangle. Meanwhile, the initialization step processes each rectangle exactly once, resulting in linear time complexity. Combining these factors, we can confidently conclude that the overall time complexity of the solution is O, n plus m asterisk log n, where n represents the number of rectangles and m is the number of pick calls. When working on this problem, there are several common mistakes to be aware of. First, solutions often fail to handle edge cases properly. For example, rectangles with zero width or height can behave differently than expected, and overlapping rectangles might introduce unexpected complexity. Testing thoroughly with these scenarios is crucial to ensure correctness. Another frequent issue is related to probability distribution. If you select rectangles with equal probability without factoring in their area, the resulting point distribution will not be uniform, which violates the problem's requirements. Efficient preprocessing is also key. Without pre-computing cumulative areas or prefix sums for the rectangles, your solution might become inefficient, especially when selecting random points multiple times. Additionally, watch out for floating point errors when dealing with probabilities or random indices. These errors can arise due to precision limitations, so integer arithmetic is often a safer choice. Finally, off-by-one errors are a common pitfall in random selection problems, particularly when indices are zero-based but are treated as one-based, or vice versa. Double-check your index calculations to avoid these subtle but critical mistakes. Now, let's focus on some insights that are particularly relevant for interview settings. One key topic is understanding how to achieve uniform randomness when selecting points from rectangles of varying sizes. This involves ensuring that the selection probability is proportional to the area of each rectangle. Interviewers may also expect you to discuss pre-processing for efficiency. Highlight how pre-computing cumulative areas balances pre-processing time against faster query times, which is particularly useful in scenarios with repeated queries. Edge case awareness is another important skill. You should be ready to handle scenarios like non-overlapping rectangles, degenerate rectangles that collapse into lines or points, or even just a single rectangle as input. Additionally, you should be prepared to analyze the time and space complexity of your approach. For example, pre-processing might take linear time and space, O, n, while selecting a random point could be optimized to logarithmic time, O, log n. Being able to articulate these trade-offs demonstrates a strong understanding of the problem. Finally, let's discuss related problems and alternative approaches. Some problems that share similar concepts include LeetCode 528, Random Pick with Weight, which deals with weighted selection, LeetCode 497, the current problem, LeetCode 398, Random Pick Index, and LeetCode 382, Linked List Random Node. Exploring these problems can deepen your understanding of randomization techniques. When it comes to alternative approaches, one efficient method is weighted sampling with binary search. Here, you pre-compute cumulative areas and use binary search to quickly locate the rectangle corresponding to a random index. This method offers O, n, preprocessing and O, log n, query time. Another approach is direct sampling with rejection, where you randomly select a rectangle and a point within it, but reject results that don't meet the proportionality requirement. While this ensures uniform distribution, it can be inefficient for unbalanced inputs. Lastly, a grid-based selection approach can be used for large-scale problems. By dividing the space into a grid and pre-computing point densities, you can achieve constant time selection, O1. However, this method requires significant memory, making it unsuitable for scenarios with strict memory constraints. Great job! We've covered how to tackle the problem random point in non-overlapping rectangles and explored different approaches. Remember to focus on optimization and always analyze the trade-offs. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!